Hello students, welcome back. Let us resume our discussion in section 2. We are studying the law of sines. We didn't prove it yet. We are going to postpone it as much as possible. Instead, we went through some application problems. First, solving some triangles. When two angles are known, consequently all three angles are known, that's a standard case. That's easy. If only one angle is known, things can get a bit trickier, and in some cases we have unique solution, some case we don't. Sometimes even no solution. Beware of those kind of things. Alright, now let's go to a little bit more realistic application problems, which I regard even more important. Here's the first problem, very typical law of sine problem. A pilot is flying over a straight highway. He determines the angle of depression of two mileposts A and B that are 5 miles apart to be 32 degrees and 48 degrees, respectively. Find the distance of the plane from the post A, and then find the elevation of the plane. So let's say this post is AB and the cockpit of this plane is C, capital C. And we have triangle ABC. And then small c, opposite of angles capital C, is 5 miles. And angle A is 32 degrees. Angle B is 48 degrees. See that? Well, maybe a simplified picture will be more helpful here because 3D pictures over there look nice, but it gives you too much information. So 5 miles and A is 32 degrees because these two are parallel, and 48 degrees, and cockpit is right here, and the problem is asking to find out the small b, the distance between the airplane and the milepost A. Okay, how do you find out B? We're going to use the law of sines, of course. Oh, before that, let's find the third angle actually. Two angles are there, and the internal angles of a triangle add up to 180 degrees. So finding out the third angle is easy, straightforward. So we have 100 degrees, alright? Now, let's set up the law of sines. So, A over sine of A, B over sine of B, C over sine of C, all three are equal. That's the law of sines, isn't it? And then here, let's put some numbers in. As a matter of fact, no, before doing that, let's see, we're looking for small b, and small c is known, and we are not doing anything to A, so let's take this one away. Alright, and then let's put in some numbers. So, angle B is 48 degrees. Angle C is 100 degrees. And C is about 5 miles. And B, that's a question. And then now all these are observations, measurements, so none of them is accurate. So to be a bit more proper, we'll have to change this equality into approximate inequalities now. Alright, let's solve for B. All I have to do is to flip this to the other side, right? Okay, let's go ahead and do that. And flip this sine of 48 degrees, that one, to the other side. And there you go. You solved it, and all you have to do is punch this into calculator, and you're going to get your B value. Let's open this cell, and let's check what I did. Alright, exactly the same thing. I solved this symbolically first, but no difference there. And then punch in the calculator, I'm getting 3.77 something miles. Alright, now what do? We got this So part 1 of the problem is done. Part 2 of the problem, that's the elevation. How do you find it? Well, if you focus upon this right triangle on your left, then we have 32 degrees here. Hypotenuse, we just found out, 3.77. And opposite, well, we can find out. We can use right angle trigonometry here. This green triangle with hypotenuse 3.773 and the angle 32 degrees, looking for the opposite. So sine is h over b. So h is b times sine of a. Put the numbers in and run your computation. You're going to get about 2 miles. Alright, want to try this again? This is very, very typical law of sine problem. Okay, alright. Let's try another problem just like this. Let's go up to section 1 and then let's reopen this flagpole problem. Previously, we used tangent method. Remember that? Here's a picture. Yeah, and small a, small b here add up to 60 feet. That's how the flagpole is tall. And then from blue triangle and red triangle, we have these tangent relations. Because we don't know the hypotenuse, all we know, adjacent versus opposite. So tangent of 18 degrees is a over x, tangent of 14 degrees is b over x, and a plus b add up to 60 feet. So how do you find x here? Well, this is a system of nonlinear equations. We'll have to solve for variables, plug in, and use method of substitution. So solve for a, solve for b, put those in, then I'm going to get a and b are x tangent 18 degrees, x tangent 14 degrees respectively. So they're going to add up to 60. From here, factor x out and we have a numerical quantity. So x times this number is 60. All we have to do is to divide by that. We get the answer. Nice, but wow, this was hard. Is there any easier way? Yes, there is. Let's approach the same problem, this time using the law of sines. So basically, we are looking at this kind of picture. This time, I'm going to label capital A, capital B, capital C as the angles. And small a here is 60 feet, the entire height of this flagpole, alright? I'm recycling this small a as previous solution, so it may cause confusion. Hopefully it doesn't. Alright. So a is 60 feet, small a is 60 feet, capital A is, let's see, 32 degrees. And then if you look at this blue right triangle, 18 degree here, 90 degree here, so you can find this is 72 degrees. 90 minus 18. Similarly, 90 minus 14 degrees, you're going to get 76 degree here. 14 degree here, 76 degree here, and here right angle 90 degree. So we have all the angles. A is 32 degrees, B 76 degrees, C 72 degrees, and small a 60. Yeah, this is typical law of sine. So law of sine, A over sine of A is B over sine B. I don't have to use C. Let's just focus upon this, B. And solve for B, plug in numbers and solve for B, as we did before. Flip the sine of 76 degrees to the other side. That's what you're going to get. 109.862 feet, approximately. Okay, alright. We got this. We got this B, hypotenuse. So let's focus upon this blue triangle, blue right triangle over here, hypotenuse B, and then x is opposite of this angle C, so you can use law of sine here. Excuse me, did I say law of sine? No. This is law of sine. This is just sine function of this right angle trigonometry here. Blue triangle. So solve for x. X is b sine of c. C is 72 degrees. Plug in the numbers and do your computation. Another way to do the same thing is to use this 18 degrees here. In that case, you can get extra cosine. So you can get cosine of 18 degrees is x over b adjacent over hypotenuse, and then you can go from there. It'll turn out, of course, cosine of 18 degrees is equal to sine of 72 degrees because they're complementary angles. So we just went through two typical examples of the law of sines, and both were acute triangles. Now, let's begin a problem with an obtuse triangle. Here we go. Stop the playback and think about it. A tree on a hillside casts a shadow of 215 feet down the hill. If the angle of inclination of the hill is 22 degrees to the horizontal and the angle of elevation of the sun is 52 degrees, find the height of the tree. Compare this problem with the previous problem from section 1, this one right here. This one is a lot easier because we have this tree lying on a flat ground. So we end up with a right angle trigonometry, not an obtuse triangle. It's much easier this way. You just have tangent and that's it. This one is much harder. It's not a right angle trigonometry. We have an obtuse triangle. So how do I work it out? Well, this simplified picture will help. So we have obtuse triangle, and then we can consider imaginary lines on the ground. So okay, we can extend this horizontal on the ground. We can extend this vertical along the tree on the ground, and we have these dotted lines. And then let's see, total 52 degrees here and 22 degrees here. So subtracting 52 from 22, we get 30 degrees here. See that? 52 degrees of angle of the elevation here, minus 22 degrees, so we get 30 degrees there. Okay, we got one angle. How about the other angles? Consider this big right triangle. This is 52 degrees, so I can find out A. 90 minus 52, yeah, we can do this computation. 90 minus 52, 38 degrees here. And then B, we already discussed it, 52 minus 22, 30 degrees here. And C, yeah, it's easy computation. Internal angles of triangle add up to 180 always. So do your computation, you get 112 degrees. So we have this obtuse triangle. We identified all the angles. And then we find B. Small a we know. We find B. Can you set up the law of sines and find B? No problem. A over sine A, B over sine B, and so for B. Put the numbers in. A is 215 feet, and then capital A and capital B, that's 30 degrees and 38 degrees respectively. Punch in the calculator, you're going to get about 175 feet. Alright, so much for the second problem. I'll leave the third problem to you. Another obtuse triangle. And by the way, did I say this was acute? Sorry, this is an obtuse triangle too. Over here we have 100 degree. It's just that the triangle's positioning was a little bit easier.